for your participation at this new edition of this international exhibition in Bergamo. Because environmental protection is now the most important topic of oil and gas industry, I am pleased to introduce the theme 3 on fugitive emissions and valve sealing technologies. First, we will have a presentation from Mr. Philippe Burlot from Saint-Gobain from Belgium. That's correct? Yeah. Following, we will have a presentation from Christian Salvatori from Italy, Victrex. Victrex CT polymers for more reliable seals in cryogenic conditions. Sorry, I forgot the presentation from Saint-Gobain. So it will be a systematic approach for pre-validation of polymer spring-energized seals for critical valve applications. Following, we will have a presentation from Dave Anderson, but apparently Dave Anderson is not here at that time. We will see. From United Kingdom, SCORE Group, presentation of emissions elimination. Why reduce emission when you can eliminate them? Following that, a presentation from Nikolai Teska from VED COEMI, valve's role on environmental protection. Following a presentation from Laurent Guimet from France, Technetics Group, semi-dynamic metal sealing, base theory and example of valve applications. And to finish, a presentation from Loïc Deneville, France, Total Energies, in collaboration with Eric Sauger and Jérémy Leray from Le CETIM, a famous great laboratory in France. The presentation will be the comparative study between IOGP and ISO valve fugitive emissions requirement. I think that we can now start with the first presentation. Mr. Philippe Burlot, it's to you. Normalement, on doit pouvoir suivre.
Merci Christian. Hello everyone. Sorry. So I'm going to start on spring-energized seals for LFE. So the base idea here is to have a pack, a seal pack basically, that would replace the current solutions, graphite packing, but being self-energized solutions that then do not need to be compressed actually, because it would just work with the pressure, and then this will lead to a simplified hardware design with reduced length of the shafts in the system around, and there would not be needs for a secondary sealing arrangement then. And of course, since we are talking about PTFE-based solutions, we would have low torque during operations and a long lifetime with reduced wear. The scope of the project is, as you can see, compliance with Class A on the ISO 15848, with a temperature range from -50 to plus 160 degrees. Conditions are here on the right side. Pressure up to Class 2500, water tone motions, and C01 type of test, so 205 cycles. On the left side, what you can see is the design that was developed in 2014 for the Class B. And of course, given the context, there's a need for A-class solutions. Yeah, this is the whole presentation. So we decided to take an approach quite systematic, starting with simulations, and then internal tests of our solutions, and then go on the qualifications of a real valve. So first, the simulations. We at Saint-Gobain have developed our own polymer-based solutions and characterize all of our materials, basically, for simulations. We have a full database that ranges from liquid hydrogen temperature up to plus 260 degrees plus for certain materials. And then we can easily simulate all the elastoplastic behaviors of our seals and try to optimize for each seal design the contact profile in terms of contact length, load distributions, then have an idea of the wear rate and the torque that would be supplied on the system, basically by the seals. So then once we have run some simulations on some designs, we have optimized more or less the designs, we put some designs in tests, so we could do a pre-selections. We have internal test capabilities where we have here on the picture you see a climate chamber with inside our test cell. On top of the climate chamber is the actuator, so the quadrotor motions. And behind there's a helium bottle where we can control the inlet pressure, of course. And on the right side in the red there you have the mass spectrometer. So basically our seals are fully tested in temperature, in full temperature and pressure range. Just a word on the measure of the fugitive emissions. So you have two techniques. One is the vacuum method, so the most accurate method. The one where all the leakage is captured in a vacuum chamber and directed to the mass spectrometer. And then you have the sniffing methods, which is still, well, we just come with a sniffer from the mass spectrometer and try to capture as much leakage as we can, which is quite okay for the class B, but has some limitations from the class A. So you have some way to tweak these sniffing methods by trying to bag the leak rate and trying to collect it, but still, it's still not as accurate as the vacuum methods. So that's why we went for the vacuum methods. And so you can see here on the left our testing cells, where you have in green the seal that is facing upwards, with the inlet pressure coming there. In our test here, it's 25 bar pressure, and behind the seal, so on the bottom there, you have the vacuum chamber that leads to the mass spectrometer, and then the shaft that is inside, and it's just having a quadrotor motions on a C01, so 205 cycles again. So you can see the results on the right of two different seals of the same design, where in blue you have the temperature profile. So on top it's from plus 20 to minus 45, and on the bottom it's from 20 to plus 160. And in yellow, yeah, it's yellow here. In yellow you have the class B, so the limit of the class B. In red you have the limit of the class A. And in orange you have the measures that are done before and after each cycling, so at the beginning and the end of the temperature plateau. So you can see that for both tests, internally we're passing the class A solutions. So we took profit of a test that we were doing for something else on a ball valve, a 10-inch ball valve, that was then tested in cryogenic conditions. And here, as you can see on the picture on the right, we used the in-between solution, so a bag sniffing method. So it's not as accurate as we would like, but we could see that for all this test protocol, we were passing the class A. Since we were not really pleased by the results because we could have done better, let's say, we decided to go for full qualification, so third-party testing that would then deliver a certificate. So you have an example on the right there. It's a little bit small, but and as you can see, we already have a successful certification completed for low temperature, so minus 40 to plus 40 Celsius, and the work is ongoing for the high temperature range. So just a small picture of the solution today. As you can see, it's spring-energized belts. So as we said in the beginning of the scope, then it's energized with the pressure. So you don't need to torque it every time. You don't need to control it. As long as you have pressure, then it's energized. You have multiple sealing barriers, which is asked by the standards, and then helps at reducing the low emissions. And again, since it's polymer based, then it's low friction and low wear. And now, as we are here to talk about fugitive emission, let's talk a bit about also what's coming in the future of emissions. We are moving more and more towards the hydrogen industry. So hydrogen for us it's not something new. We already have solutions in sorry, as you can see on the left in the full range, I would say, of the hydrogen markets, going from liquid hydrogen to hydrogen gas and low pressure to high pressure, whether it's from space applications or electrolyzers or any other kinds of or pumps and compressors. So we can be everywhere there in that square with all the product range you have there. So either polymer seals, metal seals, our own grades of polymers. Of course, we know that there are some challenges coming. So just being there in the market doesn't mean that we can just rest on that. So that's why we are constantly developing, well, trying to understand more and more our materials and trying to be sure that we're selecting the best material for the best applications. And that's why we're constantly testing our materials for hydrogen today. So I show you here on the right the test campaign. Few tests to be sure that then the solution is fitted for either really low temperature or really gas decompressions, permeations, all this effect that we know that, for example, on some elastomers are really critical, that some elastomers cannot cope with these temperatures or these gas compression and decompressions. And that's where we are trying to develop our, well, to make this test and really make sure that we are covering everything and there's no problem for anyone. And again, try to reduce as much as possible fugitive emissions on hydrogen. And as a last word, I would say that well, we all know that today green hydrogen it's not going to be ready today, basically. So we have to cope with gray hydrogen and as much as possible blue hydrogen, where we actually try to capture the CO2 that is emitted by the methane cracking and try to make it as close to green as possible. But then capturing CO2 means challenges for the system as well as for the seals. So that's why we also went to full test campaigns on our materials. So we already qualified quite some materials for CO2 applications, to 100 CO2 applications, pressure up to 300 bar, temperature ranging from -30 to plus 130, and then in the stage close to the supercritical stages, where actually we know that it tends to dissolve some polymer materials. So that's where we can play a role in here as well. And that's it, because we're good.
If somebody want to
The
a question for Mr.
No, yeah, doesn't work.
Maintenant? Grazie. Hello, Philippe. My name is Kyle Daniels. I'm the president and CEO of Clark Valve. We've been using spring-energized seals in our valves for many years, and we have certifications on that for ISO 15848 as well. And I had a question. Your certifications were for helium and not methane.
Yes.
and of course, helium is a smaller molecule. So if you can pass helium, of course you can pass methane as well.
That's the base idea, indeed.
So I just didn't know if you had also done the methane tests just to have a result in specific parts per million?
Not today, no. As you said, helium is the most stringent. We always try to go for the most stringent just to make sure that there's no problem with or no surprises. So in the end, yeah, we focus on the helium. Yeah.
And just for reference, since we use the same sealing technology, we source our seals from Ball Seal in the United States. We're not the manufacturer of the seal, we're the manufacturer of the valve. But we find your seals interesting. We passed the certification for methane at 2 parts per million after 100,000 cycles. So that's the CC3 rating. I see you have 205 cycles. With these seals, it is possible to go to 100,000 cycles, which under ISO is 10 years of use. So as you said, they have a very long life, very low wear solution. So we've gotten 0 emissions results. Actually, our certification is 2 parts per million, but we have field results at 0 parts per million of methane, in particular with Eni here in Italy. And they presented our results at ADIPEC, 0 parts per million after 1 year of use. And so this spring-energized seal is a very important solution for all of us to recognize. We're using it successfully for many years. So just main question was the methane, but thank you.
Okay, good. Thank you.
Thank you. Other question? Yes. Okay, now seems to be okay. No question for Saint-Gobain? Mr. Sauger.
So, Emmanuel Sauger from City. Just a question. We talk about the fugitive emission, but what about the friction? Do you have an idea? Can you give us an idea of the friction you have with your seal, please?
We do have measured this in the lab. I don't have the value on top of my head, but we can definitely get back to you on that. There's no problem. But yeah, sincerely, I was not the one following those tests, so I can give you some values, but these ones it's not really the one that I have. No, but yeah, we definitely have it. That's the base idea of doing it at home. You know, that we can implement whatever we want on the test. So it's definitely something we're looking at indeed. But yeah, to give you an idea of the value today, sorry. But I can get back on you.
Hello. Hi, I'm Claudio Ripamonti, BP. I've got a question on the design. Apologies if you explained it already. The tulip seal you put at the bottom of the seal. I've seen they are basically tulip seal with 2 different types of spring. Okay, and in my experience, either you use one or the other, because when you have the cylindrical type of spring, you don't usually use the other one. In this case, you put a combination of the 2. Can you explain what the rationale is behind the choice? Or maybe that's your proprietary information. I don't know. If you could share something more, that would be interesting.
Well, the base idea is always to multiply the barriers, and of course, there's no seal that is 0 leaking. Basically, 0 leak rate doesn't exist even for metal seals. So you always have a bit of leakage, especially with the motions. So that's why you have 2 jackets that will then be energized by the pressure gradually. The second one being less stiff, so it would need less pressure to be energized, but then it will help at bringing a second sealing barriers. And with all the sealing barriers, you're just creating bridges of delta pressure, bringing it to close to zero, and then having, well, fugitive emissions then. So that's the base idea we have behind. And then the different cavities, it's because then since they are in a row, then it's more, I'd say, yeah, it makes more sense to make it in that way than having twice the same kinds of cavities, basically. Because the loads are transferred, and to make sure that it's not getting damaged by the loads or the different movements and things, then it's better, I'd say.
Thanks.
Good morning, Nicola, Fabio, James Walker Italiana. Thank you for your presentation, first of all, interesting. And you have said that you have already materials and sealing solutions for the hydrogen application.
Yes.
Yeah, but at the same time you said also that you have already started campaigns to understand the behavior of the sealing solution that you have in order to acquire knowledge and so on. So where is the border between these two statements? First question. Second question is, what do you expect in terms of fugitive emission when H2 is there compared to helium in this specific instance? Thank you.
So first questions. The hydrogen market for us is quite old. I mean, we've been there in space for quite some years, and yeah, diverse solutions for that. The problem that we see with hydrogen today is that some people are used to use elastomer and they have sudden failures with elastomers because basically it swells up, which just acts as a sponge, just gets a lot of hydrogen in there. So in terms of permeation, it gets also quite bad. So fugitive emissions that were quite good with simple elastomer solutions on helium or methane, today it's not good with hydrogen. And the problem is that once you release the pressure, it tends to just crack. Basically, it blisters and cracks. So that's the problem with this. And we are facing more and more questions like, are you sure that your polymers are not suffering from that? We are quite sure, but we need proof, basically. So that's part of the test that we're doing, just to show proof that nothing is happening. I mean, you can look in the literature, you will find it. You can look around, you will find it. You can see all seals that we used, you will see that nothing happened, but we need proof. So then part of the testing is that. The other part is really, as I explained, we're doing some simulations to optimize our designs. And to do simulations, you need to have a clear database of behavior of your material, just to be able to reproduce it. And if you want to do that, you have no choice but testing. Basically, testing a lot in all conditions, and then make sure that your system is working correctly. So that's the second point for it. And in terms of fugitive emissions today, we still did not test it in the right conditions, like these kind of conditions. But we are quite confident again today. Again, we've been working in space applications for years, and we have quite some levels of qualifications there. You know, some stringent demands, and we never had real problems. I mean, so we are quite confident on the solutions. Now, to give you a value today, again, I don't have it on top of my head, but it should not be too much of a problem.